All right, welcome back. So, in the last video, we did the problem one in Project Euler, uh, and now we're going to move on to problem two. So, let's see where we were. We have the problem mapper, which we created, which will return whatever problem the user has entered into the command line. It'll try to look for it in the switch case, and if it finds the solution for it, then it'll just turn it to them. It'll return this. So we can create a new case here for problem two, and we can use the same file for now as long as it doesn't get too cluttered. Uh, let's just call. We have to look for what we need, what we want to call it. But this is essentially the setup that we have. Let's look at the problem two. We have even Fibonacci numbers. Each new term in the Fibonacci series is generated by adding the previous two terms. By starting with 1 and 2, the first 10 terms will be this. So each next term is the sum of the previous two terms. So 1 and 2 gives 3, 2 and 3 gives 5, 5 and 3 gives 8, 8 and 5 13, and so on. So this is essentially, we can extend this series as much as we want. By considering the terms in the Fibonacci sequence whose values do not exceed 4 million, find the sum of the even value terms. So if we were to, instead of 4 million, have it 50, so uh, consider the terms in the sequence whose values do not exceed 50, which would be until 34. And we want to find the even value terms from 1 to 34. Sum them up, and that's our answer. And instead of 50, we are having 4 million here. So we're essentially, our input is going to be 4 million or 50, and we're expecting the sum of all the even value terms. Uh, so first, I think we're going to have to look for a way to generate the Fibonacci sequence. I think that's it. And then we can sort of look for the even value terms and so on, and sum them up. And it will return an int. And for now, we can just return 0 there. So in this case, the input would be something like 50, or it would be 4 million. So based on this, we can write our tests that we've been writing. That's essentially the plan. Like, we're trying to build the whole habit of developing or writing code, and also writing tests for the code. So I guess we can just copy and paste these for now. Uh, Fibonacci. We can have the same structure here. If we were given 50, then we can like figure this out, but the next one would be 4 million. Can we do this? Something like Rust? I don't know. We'll figure out if it works. But for now, both of these tests will fail. Uh, but when we have set it up correctly, then we have the function working. It should give us the right answer. Make test. I guess it'll work for now. It'll just, no, it didn't. Because we have the wrong function here, Fibonacci. There. It should pass because we are returning 0 here and we're expecting 0 in both the test cases. Anyway, so now we are going to move on to actually writing the logic here. So let's think about this. First, we will need the Fibonacci series, which will come from some function. We'll just call it Fib series. And this should give us uh, like 1, 2, so on, uh, to n, where n is less than the input, right? Because if we were given the input 50, we need the series till 34. So once we have that, we'll probably pass this series into a summer uh, with sum function, which will take the series. And I know this is like showing us all of the errors because we don't really have all of this stuff. We're just making it all up. This is good for like prototyping or like writing out pseudocode for yourself just to give out the structure of the code that you're looking for. So basically, there will be two parts to this. One will be where we generate the series, and in this we will need to pass the input because we are comparing it with the input. The function will need the input. And once we have the series, we'll have some sort of a summer, uh, which will, whatever we get from this, so this would be sum, uh, and then we can return the sum. This will be our integer answer. Uh, cool. So now we can go on and, uh, let's see, now we can go on and create these functions. So the way I like to do this is, since these are essentially utility functions, I like to create a utils. And then in this, we can have utils based on the problem that we are trying to solve. So all of these utilities will be related to the Fibonacci problem. So we can have like package utils here, and we can have the function here, which would be fib series. It will take an input int. It will return a list of int, and for now we can just return an empty list of int. Will that work? Don't. Will this work? I think this should work. Yeah. So that's the first function we needed. The second function we need is the sum, which will it'll take the series uh, int and it will return an int. For now, we're just returning 0. And I don't really know what the convention is with Golang. I think we use uh, camel case. I'm not sure. So I'm just gonna start using camel case. That's not the spelling that works. Oh, oh yeah, it needs two C's. I can just call it like fifth series then, easier to work with. Good. And now we can import all of the functions there, which we can, the easiest way to do it is just let VS Code do it for you. So we can do something like fib.fib. No, that doesn't work because we'll need to import them manually. So we can do import and then we'll need to write the whole path to our repository. Mm, over the Project Euler go. And then it'll be utils. Cool. And from utils dot. This makes sense. So let's think about how we can actually implement the Fibonacci series. So there are two ways, essentially two popular ways to implement the Fibonacci series. There's one recursive way of doing this, and there's a regular way of doing this, which will just do it in one loop within the same function. So, and the one that's recursive, if series recursive, we're gonna implement both, uh, just in case, like just to learn about both of them. But the one that's recursive has exponential time complexity, and this one is a lot simpler. So at the end, we're going to end up using this, but I'm just going to implement the recursive one as well, just so we have the comparison. In the recursive ones, let's just start with the recursive one for now. What will happen here is we have an initial value. So if we look at the Fibonacci sequence mathematically, we have two numbers. and the next number is the sum of the first two numbers. So what's essentially happening here is, let's say that if we're looking for f of n, then f of n is the sum of f of n minus 1 and f of n minus 2. Yeah, so this is essentially what we will be doing with this whole function, because still, functions are pretty mathematical. Like, this is essentially what we are looking for from this recursive function. So we will be calling this function for input minus 1 plus input minus 2. This will be returned. But if you look at the function itself that we've written here, the mathematical ish one, the result of this whole thing is a number. It's not a list of numbers. And we have defined a list of numbers. That's why Golang is kind of freaking out. Like, so if we were to implement this, we'll need to modify the return type by a bit. If we were to make this just an integer, then this works. Then this doesn't cause any problems. And our original mathematical definition of uh, a Fibonacci series, which was this kind of works. This is essentially what this function is implementing, right? And Golang is kind of freaking out because this is an infinite call. So we'll need to have some place where this can stop, because this will just go on forever. So we need like a stop condition, a break condition for this loop, this recursive loop. So what we can do is, if the input is less than 1, or if it's less than equal to 1, then we can just return 1. And this is essentially what our Fibonacci series is, because if you look at the Fibonacci series itself, it ends at 1. So what we are telling is, if the input which we are getting in, if it's less than or equal to 1, just return 1, which is the stopping condition of the Fibonacci series. If we were to start here, we go backwards until 1. If that's not the case, then just do that. The recursive call to the function itself. So if we were to call this from our function utils.fibRecursive, and we were to give it 5, and we do a format print, we need to return something. So we'll just return 0 for now so that these things aren't executed. We'll do a make run. Oh no, we'll have to do a make run of the problem, which would be 2, and input doesn't really matter, so we'll just do 1 then. I think we'll need to return the input itself whenever we get input less than equals 1. So if it is 0, then we will return back 0, because we need to consider the cases where it goes below 1, and we just return 0 in those cases. Yeah, so now when we try to print, uh, say, the fifth Fibonacci number, or the fourth one, the fourth Fibonacci number, I mean, considering that 0 is a number that you're counting, then 0, 1, 2, 3, that's the fourth number. If we were to do 5, then it should print out 5. Similarly, whoops, yeah, we could do something like this. This makes our life a lot easier. If we were to do 10 here, then the 10th number is 55, which is here, and our 11th should be 89. So this gives us the nth Fibonacci number in the series. Now the question is that we need a list of Fibonacci numbers. We need that. How can we do that? So one way to do this would be to, within the uh, within this function, we can run a loop. So we can do something like for I uh, in 0 I, because we are hmm, Yeah, so in this function, we can like run a loop, uh, and we run the loop until the Fibonacci number that we receive from this recursive function uh, exceeds the input, and when it does, we just break the loop. So we can do something like for. So we'll call Fibonacci series. We will incrementally pass numbers to it. So we can start from where I int is that. Okay, it's not used. So we call that. We capture it in the fib, like the current fib, and we check if the current fib is greater than equal to the input, because it is saying that do not exceed 4 million. So if we check that if current Fibonacci is greater than or equal to the input, then we just break. And if it's not, then we need to append it onto like a series that we're keeping track of in this function. So instead of doing all this, I think we can move this to a different function, like here, like func fib series collector. We can do this. We pass the input, and this will return us the Fibonacci sequence. We pass in that. This will be an array, and whenever it's not the case, then we just push. How do we do this? Is there a push method? Is there an append method? Yeah, but I think append, what does it do? It appends a slice, I think. No, it appends elements. Appends elements to the end of the slice. Yeah, this works. So we'll need to append the current fib onto the fib series. Does that work? Uh, okay, value of the thing is not used. So at the end, we'll just return the fib series, and we don't need that. And oh, cool. So we'll need to collect this into the same variable name. So fib series will collect whatever the result of the append is. So this works. Now this essentially is our fib series method. Uh, let's just see fib series. We can call this fib series recursive, and this can be the recursion, fib recursion. And this doesn't we're not exporting it, so we can have so if you don't know, if we have like a function name starting with a capital letter, then it is a public function which gets exported to other modules. But if it's not, then it doesn't. So we can keep this function as a private method because we're not using it outside of this module. We're only going to be calling this that function, and this will call fib recursion. Cool, this makes sense. So whenever we call fib recursion, it'll return us the Fibonacci sequence, which will be generated using recursion. And we can comment this out. We can, instead of calling fib series, we can call fib series recursive. Is that the name? Yeah, it is. And now we'll need to write the fib sum function. Now, this one should be pretty simple. We are essentially looping through the Fibonacci sequence, and whenever if that's not the function, whoops, this is the function that we want to implement. So we are looping through the Fibonacci sequence, and whenever it's even, we just add it onto the sum that we're keeping track of. So let's see how we can do that. We can like use the range. That's probably the easiest way of doing this. Uh, and I always forget which one is the index and which one actually gives us the element. Let's see. And this will be the sum where in sum. where sum, sorry, and we will add it on to sum if I is divisible by 2, then sum plus equals I, and at the end we just return the sum. Now let's see. So when we give it the input of 50, then format imported, yeah, not used. It's going into some kind of an infinite loop. Let's see what's happening. Let's see how many times we're actually calling this. Uh, we have it for int I equals 0 to, oh yeah, we're not incrementing I, which is why that's messing it up. So we'll need to increment I. What's it suggesting here? Simplify range expression. How can I do this? Let's fix it. I don't know. I don't know about this. Let's see anyway. 20. So yeah, that doesn't seem right. So essentially what it's saying is everything from here to here, all the even numbers summed up is 20, which is clearly not correct. Let's see what the Fibonacci sequence we received is. Is it the correct Fibonacci sequence? Format, print line, the series. So this is the SPIP series that we're receiving, which looks okay. It's less than 50. But clearly the range thing which I just changed is messing this up. Let's see why that's happening. So I here would be the uh, okay. So I is the index and V is the value. So will it be like this? Is this the right way to do it? Yeah, it is. So you're adding 2, 8, and 34, which is 44, which is correct. 2 and 8 is 10, plus 34, 44. This looks good. Now let's try giving it 4 million. I think this will be tough because the recursive function, it has an exponential time complexity, so this might take a while. No, it didn't. Let's see if this is the right answer. It is cool. So the exponential time complexity one worked. I'm just going to add these values to the tests over the values, in the value for the actual answer. And here it was 44. And now when we run make test, this should work. Yep, everything's passing. So cool, that's working. Now we can move on to the actual solution, which is the most efficient solution. What we will be doing here is we will like keep track of the the uh, current values of the series. So if the series is let's say 1, 1, 2, 3, 5, 8, uh, then what we are doing is we store 1 and 1, and then we figure out what the value uh, of the next value, what the next item in the series would be, and then we store that in one of the values, and then we sum these up, and then we get the next, and so on until we find the nth item in the series. So let's just call this fib, uh, just like we called fib recursion, we can call this like fib optimized, which will take an int and it will return an int. And this will essentially give us the nth item in the fib series. So what it does is it keeps track of, as I said, we're keeping track of two numbers at a time. And the current length of the series would be 2. And we what we are doing is we are going from the count to the input while keeping track of these two variables of the series. So we'll just do like while for count less than equals the input. So this is kind of how we write while loops in Golang, which is a little unique. Uh, we give it the condition here. Usually, this is how while loops work. While this condition is being satisfied, run everything in this, and this is how we write while loops. We're not like initializing any value and like doing something at every step. Instead, we just give it the condition, and while that condition is not satisfied, it'll just run everything in the body. So what we're doing is we need a temporary, like a temporary place to store a plus b, and then uh, a would be temp plus b, and b would just be temp, right? So let's say that if a is 1, b is 1, then c, the temp would be 2, and then we set a to 1 plus temp, which would be 3, and then b would be temp. So essentially what we have done is we are trying to replicate this behavior of the series where, and now we have the whole series as it is generated. And at the end of this, we will have we can like return b, which would be our nth Fibonacci number. And at every instance, we also need to increment the count unless like we want this to go into an infinite loop. So we can use that now, and now that is generating the nth Fibonacci sequence. But here's the thing, it's also generating the Fibonacci sequence itself at every step. So what we can do is keep track of the series itself. Why not? Uh, this would be aware of the series, and at every step, let's say that we append, at every step we'll need to do something like this. We'll append a, assign it to fib series itself, we append b, and at every step, instead of doing this, we can do this and this, and fib series equals append a, because at every step we are getting a plus b in temp and we are assigning it to a. So the third Fibonacci number would be in the Fib series that we are keeping track of, and we'll need to modify this condition to, uh, or we won't. This will return us the, let's say that we input 3, then it will return the first 3 Fib series to us. But we don't need this. We can just copy this into the function itself, and we can modify the this thing a bit. So let's see, we want the last element of the fifth series to not be, to not exceed, uh, we do this, and fifth series minus 1 is less than equal, is less than equal to the input, or not equal to, we don't want to have that, right? And we can return fifth series. I hope this makes sense. So uh, we're keeping track of the fifth series here. We're having two variables. I guess we can get rid of this later on. We don't need these variables. We can just use this array to keep track of everything. So we can do something like this, where we would have 1 and 1, and we get rid of those. We don't need to append anything because we already have those numbers. We're not keeping track of the count anymore. Temp would be fifth series, length of fifth series minus 1 plus fifth series of length of fifth series minus 2. Yeah. Uh, and let's see, we don't need B anymore. And we're not using that. And we just append temp. So we're initializing the fifth series with 1 and 1. And while the last element of the fifth series is less than the input, we we do these two steps where we get the temp, uh, we add the last two elements of the fifth series to temp, and then we append temp onto the fifth series. This is pretty simple. Like this is a lot simple than what everything that we've done so far. This is a lot more rudimentary and easy to understand. Uh, so this returns the fifth series. Now, another thing that we can do is we can just pretty much solve the whole problem here while we are generating the fifth series. But since we've given the premise where this is our structure, we can return the fifth series and then find the sum. Otherwise, if we wanted to directly uh, have conditions such as if temp is even, then then add it onto a sum variable that we're keeping track of, then we can do that and return the temp or the total here directly. But since we already have a fixed sum and everything, so we can let it be. Let's try doing make, but before that, we'll need to comment this out. And now we're generating the fifth series in a completely different way. We're doing fifth series and we're passing the input. Let's try make run with our initial 50. Yeah. So now we're using this function to generate the Fibonacci sequence, and we're getting the sum of the even numbers. And we can do the same with the 4 million. And this should also work. And now when we run make test, all our tests should be passing, and we are good to go. Awesome. So in this video, we've essentially learned two different methods of implementing the Fibonacci series. One is the recursive one, and one is the sequential way of implementing it. The sequential one is a lot more efficient in terms of its time complexity. So yeah, thanks for watching. Catch you in the next video.